Hello from your favorite artist electronist, Mr. Q12 here. I made an experiment. I wanted this experiment to do it for a very long time actually, and I tried a couple of times, and I was afraid, and I also didn't know, I didn't have the knowledge, and I failed a couple of times, to be sincere. Relatively recently, a couple of, I don't know, months, weeks or months ago, I tried to run at a higher power, voltage regulator, an LM317, and I stumbled over some problems from this breadboard, some problems from this, and from the design of the thing that I was trying to make itself. I got some issues, and partially I started to see and discover them bit by bit from practice. And everything I'm showing you here is from practice and not from some weird theory. So after that relatively failure experiment that I did with the LM317 voltage regulator to boost the power from it. This is actually the history. I started that LM317 voltage regulator. I tried to make it work and to find at what power it is good for to run by itself alone. And after some discussions with my friends from the AAC forum, I believe it's an American forum, but after some discussions there and with my UK friend, so everything together accumulated. And my friend, I believe he's an American, and we were talking about that LM317, and he gave me an idea to build a power and current tester. So what this circuit is here is a current load tester. So when I'm increasing this potentiometer, you can see it here, this potentiometer, when I'm increasing the value from here through this op-amp, which is driving this little transistor, which is, where are you? Here it is, there, that little one, which in turn is driving this other transistor, which is this bigger one that I'm holding my finger on it. And then this R6, which is this bigger load resistor, you can measure the current over from this point to that point there. So between these two lines. And every time I was getting exactly the same amperage that I was getting from my power supply there. So if the power supply was showing, I actually noted everything here. Okay, so here is 0.05 amps or 50 milliamps over R6. You see, this is the R6, this bigger 1 ohm resistor. Over this, I actually noted it here, 1 ohm, 5 watts, and I was getting 0.047 or 47 milliwatts. Let's say it's exactly as 50 milliamps like there, so it's 47 millivolts there. I was getting this reading in accordance with my power supply. You see the power supply, my power supply is a bit different, is having a different reading most probably than my multimeter that I'm holding it in my hands. So that's a little bit about the circuit, and I showed summarily a little bit about it. But now let's get into business actually, and I'll tell you the course of events and how I tested everything, because I started very slowly, and I was afraid all the time not to burn this power transistor that I'm having here. In the original circuit, there were other component values for these two transistors. This was 2N222, and this was something else that I don't remember from my memory. But with what I had here in my arsenal, what I used a BC548 for this smaller one. So this one here is BC548, what you're seeing, and this bigger one is this guy here, Q3, is here, BD681. And this BD681, I actually write it here, is 100 volts with 4 amps at 40 watts. So this is the power that can maximum dissipate, but usually is not used at its maximum, is under it. Probably, I don't know, half of it, 20 watts or maybe 30 watts if you can actually drive it at that very high value. So this is, remember, this is a maximum. Also here as well, this is also a maximum. You don't drive this transistor at its maximum wattage that you have there. The same pinout and the same specs is for the PNP version, BD682. So that's why I'm having this noted here as well. But what I'm having there on my board, on my breadboard, I have this BD681, which is an NPN transistor, a BJT NPN. So that's the pinout and how it's doing. And if you see how I'm having it mounted here with the back on the left side, so my transistor that I'm having here, its pinout is with the front like this, and this is the base, collector, and emitter. But then on my breadboard, I had to inverse it, to put it inverse. So right now, when you see it there on my breadboard, is with the base here on this other side and emitter on the bottom there. So that's how I have it mounted here. I will only make a presentation of what I did, because everything I have here, it remained like this because I had a serious problem, and I will discuss it later. So at this point, what I did, first of all, the first thing to test was the naked power transistor. I tested it exactly as you can see it here on the breadboard in this configuration that you are seeing here. I wanted to test it naked to see how much power can support by itself without any help from anything. So by itself, without a radiator, without any aluminum radiators like I'm having prepared. So in this case, when I'm having it like this naked, I have this list here. Let me put my ruler here. So from here to here to this star, when to this line here, vertical line, is like a column. You see, this is a column. So what I'm having here, these are constants. So from here to here, I have some constants. These are never changing here. With one exception, I believe I changed this R10. In the beginning, when I made this test with what I'm having here, I had that 1 kilo, but that 1 kilo was this here, this R10 here. It doesn't really affecting very much the power over this transistor, the power dissipation over it. It is limiting the current to its base. So having it at 1 kilo or 100 ohms as I have it later didn't really affect the readings that I'm having here. This is also constant, BC548, BD681, which was actually the testing transistor. An L6, this guy here, which here on my breadboard is this 1 ohm at 5 watts. So these are constants for this breadboard experiment that I'm doing here, okay? They are not changing at all. Ambiental temperature is 25 degrees Celsius. And how I'm reading it, all my temperature, I'm reading it with this device that I'm having here. It's called NZK, you see, TM-902C. This is the device that I'm always using. Also for the ambient temperature, I can put my probe on the table or keep it in the air, and I'm getting this ambient temperature. My power supply, I was having it at 5 volts with 0.05 amps or 50 milliamps settings, but this amperage was actually dependent on the final temperature over this transistor. Every test that I did here was around this temperature, to keep it less than 50 degrees Celsius. And the less, the better. The higher, the worse, pretty much. At this point, at this 45 degrees Celsius, I was getting this amperage, 50 milliamps, from my power supply readings from there. So here I was getting 0.050, okay, or 5. And then I started to get some voltages over the entire circuit where I thought is important. So over R10, from here to here, I took this reading, this voltage over this resistor, and I was getting 100 millivolts. And you will see with the other experiment, when I change it, exactly this resistor, I changed it from 1 kilo to 100 ohms, and I still got the same very small voltage, even though I changed its value, which is a bit mysterious. I was expecting something a little bit different value of voltage there, but I didn't. Over this transistor, collector emitter, I got 3.5 volts. So from collector to emitter, I put my voltage meter and I collect this 3.5 volts. And the base, and I forget to mention here, is to ground, base to ground. So from here to ground to here, I got 1.84 volts. Okay, and as you can see on this base is actually the output of this op-amp in the same time. So I'm shooting 2 rabbits in the same with the same reading. And on Q3, which is this, BD681, on collector emitter, from here to here, I took the reading, and I was getting 4.7, almost 5 volts there. So my power supply was showing 5 volts, but I was getting 4.7 over this. And the base to ground, so from this point to this point here, I got 1.27 volts. And for this L6, which is this power resistor, this one here, for this L6, I got the exact value, but in volts, in millivolts, for this 47 millivolts, but is the same as 50 milliamps here. So getting the reading of this 1 ohm resistor is the same as my amperage reading from my power supply display. Again, at 45 degrees Celsius, and no heatsink. I noted this here, as you can see, is naked, without anything on this transistor, by itself. He is Rambo right now. And I calculated here the power over Q3 is, I believe, 5 volts times this 50 milliamps, and I'm getting this 250 milliwatts, or 0.25. And this by itself, so let me put it here. So by itself naked is good to 250 milliwatts, which is laughable, because this, as you remember, this transistor is rated to 40 watts, you see? And this is a fourth part of a watt, from 1 watt, is not even 1 watt. So that is a very, very laughable power dissipation or power handling of this transistor by itself alone. So my next quest was how to fucking increase this power handling, how to get more power through passing through this transistor, more current and more power dissipation over it. And the next column that I'm having here with data is in parallel with what I'm having here, and it is for this transistor that I'm having here, is the same transistor, is the same BD681, and probably you can even read it like that. You see, BD here on the top, BD68, and 1 is under the screw. And with this occasion, I want to present my box, my little drawer with very mighty, powerful transistors that I'm having. But what I want to really show you is the way I catch them together, my inventivity, if you want. So I'm having here BD682, which is a PMP, all this on the back here, and in the front here, I have a label here, are the NPN ones. This is the way I catch them. I find good size screw, original screw, I didn't cut them at all, and I put a nut here. As you can see, it is barely catching all of them here. How many I have here? 1, 2, 3, exactly 10 of them I have. And I have 1, 2, 3, 4, and 5. So 50 when I bought this batch, I bought 50 NPNs and another 50 PNPs. So in total I have 100, but I wanted to show you the way, the very simple and elegant way to store them and to catch them, to have them you know, not throw away altogether, you know, but in an orderly fashion like this, with this screw inside them. By the way, this screw is 3mm, and the hole is 3mm that is having inside them, and that's it. So this is how I'm mounting it, like this, with the back, with the base on the top rail there, and this is how I was having it mounted like that. So I changed this R10 to 100 ohms from this 1 kilo ohm. So this is not a constant anymore. It varied from this value to that value. Okay, but I was getting exactly the same 100 millivolts in both cases, which is weird in a sense. This resistor here was current regulated by the rest of the circuit here. That's why I was getting this, or my reading is faulty. For sure, it should have been 10 times higher value here than here, is what I was expecting, and I did get exactly the same value. But let's get over it, because this is not really important. It's just an interesting detail that I observed. For Q2, which is this smaller one, okay, for batch change for 548 collector emitter, I was getting 2.45 volts from collector emitter here, and from base to ground 2.2 volts. So from base to ground here I was getting that value there. And for BD, which was the testing transistor BD681, I got for collector emitter 3.4 volts. So from collector emitter 3.4, so definitely less than here. And from base to ground I was getting 1.67, and for R6 I was getting 0.395 or 395 millivolts. But my power supply unit was showing me, of course, the same 5 volts, which is constant all the time, but this time instead of 50 milliamps I was having 400 milliamps. And you can see this R6, it did help me quite a bit deciding that I'm getting the same value as my ammeter was showing. You know, it's very close. It's not perfect, but it's very close. There are different reading modules inside my power supply and the digital multimeter that I'm having. And all this amperage is determined by the temperature that I was getting putting my probe. So this is my thermometer that I'm having here. So this is my probe. You see it here. It's a small ball, and with that small ball I'm putting it like that between the case of the transistor and the aluminum heatsink, and I was getting the temperature reading like that. This potentiometer here, I was dialing it until I was reading this 48 degrees Celsius, so less than 50 degrees Celsius pretty much. All this data is dependent by this value here to be less than 50 degrees Celsius. So if it's where are you? If it's 45 or 48 is good enough. It's close enough. You know, the most important thing is that is less than 50 degrees Celsius, and that's my entire point. And this is with heatsink. I even noted here with heatsink medium size, and by medium size I mean this. And now in retrospect I think this is a small size, but there is this even smaller size. You see, and this is a dinky, shitty, very useless. Now I believe is a useless heatsink. So you really need a very serious big heatsink usually. And I didn't mention this K1 and K2. They means I took the current. I get the current through the wires. So from this point I took out this wire. So in my setup here is from this junction here, which is going directly to the collector of this transistor there. And I took it out and I inserted my probes. I was reading the amperage with this digital multimeter. And I got from this point, like I said, I took out the wire and I got the reading from this wire and this link here, and I got 45 milliamps in this case when it was naked, and here 380 milliamps when it was having this heatsink. And this K2 was here in this point when I took out the resistor, and this is the resistor here, 100 ohms in this case, not 1 kilo, so 100 ohms over that collector pin, and I took that reading, and they are not that different, 100 microamps, and this is 120 microamps, but who knows. So this is the data that I collected from 2 separate tests, maintaining the same temperature, almost the same temperature, but with different heatsink and getting different power. So pretty much, and here I didn't note the power, but I had this list. I made this very stupid and simple list, but as stupid as it is, it helped me immensely because I didn't have to calculate anything in my head. I just looked here and I was comparing where I am in the big context of readings, and I made many measurements, actually more measurements than this two with different heatsinks. But I stopped and I took the data from this longer one that I had here because it was more relevant. So this, what I'm having here, I was getting the current, where are you? 0.4 there. You see 400 milliamps, and that's 0.4. This means 2 watts. Yeah. Only with this simple setup that I'm having here. At this temperature, at 48 degrees Celsius, okay? So a bit less wattage than 2 watts, maybe 1.5, and I was getting a little bit less temperature overheating there. I didn't test them like 10 minutes or so, but a couple of minutes I did, like 1, probably 5 minutes like that, but not 10. I should have tested them a bit more longer time. I only was happy when I was getting something, you know, some result. To have an idea what I did here, all these explanations, so 250 milliwatts is half of this, so it's 0.05. Here, you see, 0.05. So it's under here, is on the very top here, but I didn't notice it. So it's 0.25 here. It's very, very low. And I was getting a little bit less than 50 degrees Celsius over this transistor. And now with this heatsink, and I was here at this line at 2 watts, also at a bit less than 50 degrees Celsius. So this is definitely an improvement with this heatsink here. Next is a bit more complicated because I was discussing, I tested other heatsinks, as you can see here, but I didn't took the data from them at all. And I was reading basically what I was doing all the time. I was keeping it at 5 volts all the time. So this is very much a constant. But here this amperage was increasing more and more. So I got even to 0.6, I believe, with this one, but I don't remember exactly what I did there. But I certainly did get a bit more amperage and more power with that bigger heatsink. And to actually understand how big it is, you see, compared with my fingers, it's pretty much long as my finger. And do you see how thick it is? It's quite thick, you see? It's not like a paper thickness. It's quite thick. I believe it's 2 or 3 millimeters thickness here. So this is another test that I did. And let me put this aside. So remember, this was extremely, extremely helpful. As stupid and simple as it is, extremely helpful, because I was looking all the time and I was comparing the amperage that I was getting with what wattage it represents. And I was comparing all the time, actually. And then I built this. Actually, this took a couple of tryings until I reached this stage that you are seeing here with this clamp. And I put 2 coins. This is a coin here, and it's having another coin. You can barely see it, but it's there. You see it? Let me zoom in. But there is a coin. It says Romania. You see? Romania. It says there. And this is from England, actually. It's a coin from England, from my friend from England, a Romanian friend. It's, I don't know, £1 or something. This is a CPU radiator, CPU heatsink. It's very, very wide and very thick, very thick. And compared with my hand, it's pretty big, as you can see. It's very, very big. And I did a series of experiments. I have to explain everything as quickly as I can because I don't want to bore you to death. And I will actually put it to test. So before I was getting the idea to clamp it like this, here is my BD681 here, where it is clamped there. And I drag the wires. I put some isolating tubes on its pins and the soldering points from these wires to those pins, not to touch this aluminum heatsink because they are very close to it, especially when they are pressed like that. And so for protection there, and the wires are getting to this board that I had. I was forced to get out from this breadboard, but because this breadboard was creating a lot of problems. So let me tell you a little bit about this breadboard. What I was having, I was powering with these 2 alligator clips. I was powering it here and here. So let me move this. This is the positive here, and this was the negative. So in this configuration that I'm having here, I was having, let me move this a little bit there. What I was measuring, actually, I was measuring directly these power lines, this positive line and this negative line. I was measuring from here to here. I put my multimeter on voltage, and my multimeter, my power supply unit there, it was showing that is delivering 5 volts. But when I was measuring here and here, I was getting 4.7, 4.6, even 4.1 volts over this. Actually, I probed, I measured different points. I measured from here to there, then to here, from positive to this pin, which is to the negative, and I was getting 4.1, I believe here. I was getting a serious drop in voltage when I was measuring only the power rails. And on this wire here, it was scorched before, but that's why I put it here, because I expected to overheat, and it did overheat, not very much, but it did. And these wires here, they also overheat as well. Not this one. This one is powering the chip, the op-amp that I'm having there. So that was fine. But the other wires that I was having here, especially this from the collector, this one from the collector of the NPN, of the Q3 here. So this wire pretty much was super overheating, and this power rails also. And then I kind of equilibrated a little bit the power. I put the positive alligator clip here, and the negative I put it here. So I took it from here and I put it here. So when I was having it here, it was more close together and not circulating like crazy like that, because it was serious losses through the wires, especially from this was the main suspects that I was suspecting the most. And this is very serious thing when you have to get some important information from your readings that you have there. So this was a problem, a very big problem here with power losses over the power lines, pretty much. That was the biggest problem that I had. And with this experiment that I'm doing right here, and with my other experiment that I had with that LM317, that voltage regulator, long before this experiment. But I learned from that one, and I knew in this experiment that I'm doing here, I knew that I will have power losses on the tracks from my earlier experiment that I did back then. So that failure actually helped me immensely figuring out very quickly what I have to change here. So that's probably all that I had to say about the breadboard errors and the circuit that I did there to a point, you know. And then I decided, actually yesterday, I decided to build on its own board without to minimize the track losses, and being on its own board is having a lot of advantages. As you can see, it's on cardboard. This is a normal cardboard. This board, I have a few components here that I prepared them as well. This potentiometer, this chip here, op-amp, the legs of it. This is a testing resistor, but here, as you can see, it is 1 by 1, you know, and probably here it will have another resistor across this point and that point. And this is the level that I'm right now. This is the circuit that I'm building, and this is the drawing on a piece of paper just to see how big this will be. I will have to leave a lot of blank space here because I will have to add some power resistors, and I'm not very sure how big these power resistors are and what I will use. If I will use a brick like this or multiple smaller guys like this, I'm not completely sure. So I will leave a lot of space here, and I already find a cardboard that is fitting perfectly. It's a little bit smaller, but it's good enough. And but instead it is a little bit longer, so it's you know, it was already cut, so I will use this. I'm not completely sure if I will use it on the black side or on this wood color size. I'm not completely sure. I really need to see what is there on the especially when I'm having black on black, it's not good, and I need some contrast to actually see what is going on. Here is glued. I used paper glue, very waterly, and that's how it's looking right now, prepared on this cardboard that you can see through it. You see? Yeah, you can see through it. Oh yeah. And voila, bada bing, bada boom. I mounted all the all the pads, and this is how it's looking on the other side. These three are glued, so they will move when I will link some wires to them. But from here, it will practically have these wires from this transistor that will stay on a heatsink. So I put them large enough like that. I could have put them a little bit smaller, and but you know, to be sure, if I will ever mount a transistor here with a heatsink to have plenty of space, probably. I'm not sure why I put them so big. Anyway, but it's good to have very big pads like that. It's very, very good. Usually I'm pro using large pads, but in practice I have to use smaller and smaller, as small as I can pads. And I originally put 0.3 watts. I don't have it here, and instead of this, what I'm having here, and instead of this 1 ohm at 5 watts, I put a third of 1 ohm, 0.3. The original circuit that my friend, by the way, this is not my circuit, this is my friend's circuit, and I praise him, and he is deserving some praising, because this is a very, very nice and user-friendly circuit. I really like it. It's very easy to manipulate. It's very, very, very easy and very reliable. I really like it. So in its original circuit, his R6, that this power resistor, meaning this one here, is 0.2, and it's having a very interesting resistor as well at 8 watts at 0.2. And mine, what I'm having here, is a shit because it's 0.3, is very close to his, but at 3 watts. That's the problem. And I didn't calculate the power over this resistor, but if I remember right from our discussions, this was about 5 watts drop over only on this resistor. And what I'm having here, I'm having right now, I have 0.47 in parallel, and being in parallel, you split it by 2, 0.47 divided by 2, and is 0.23.5. So 0.23 is very close to this original resistor that he had in its circuit of 0.23 in my case. So this setup, when I had this 0.3 with 3 watts, it got hot very quickly, and I didn't stay and leave it too much to cook because I was pretty sure it will reach a stage when it was starting to smell as a burning resistor. So I took it out quite quickly. I didn't leave it to cook too much. And then I inserted these two guys here, and the 3 watts plus 3 watts, it means around 6 watts. And with this, I took another reading, a very short one actually. And this data that I'm having here is for this entire circuit that you are seeing here. This guy, the transistor that I'm having clamped there, and here, this resistor, power resistor, temperature. And over this R6, I got this resistor. I got 77. So in the circuit diagram, this is the resistor here, and this is the transistor that I'm having there. So I'm having over this resistor, I'm having 77. Actually, it fluctuated. It increased over time until it reaches 10 minutes. It increased from 75 to 77. As you can see, I erased there a little bit. And this Q3 is this transistor that I'm having it clamped there for testing. And also it got a little difference from 45 to 47, or 42, 43 to 46, 45, 46. But I leave it as 45 there. A little bit more than 10 minutes actually it was. Probably 11 minutes. I leave it in continuously, and I was checking it. I was literally staying with my finger on this guy, and here I was testing this entire radiator. And at the end of the 10 minutes, this was starting to burn me quite seriously on my finger, and I took the reading with my thermometer that I'm having here. You see, I put the probe between there, and I put the probe underneath there. But I also probed other areas of this radiator, and it until the end of the 10 minutes tests, the entire, as big as you can see it, you will expect that it will remain, you will have cold areas here on the top and very warm areas here on near that this heat source, which is the transistor. But in reality, it got quite consistent temperature all over it. So it's dissipating the temperature quite uniformly, I may add. And it's a very extremely good radiator, this CPU radiator. It has to be a very good radiator because it's used for CPUs in computers. So that's this is a very good CPU radiator that I'm having here. And it did this job absolutely brilliantly. I'm really proud of it. And the experiment that I did here. And to prove that it's working and it's not blowing up anything, so at this stage, what I'm having here, I will show some pictures, but in the end, I got 12. Actually, in one test, when I was testing this one with 3 watts, I was getting 2 amps. And with this guys that I'm having here right now, with this test that I'm having here, is 2.4 amps. So 5 volts times 2.4 watts, it means 12 watts. And I couldn't believe my eyes when I've seen this immense power handling with this tiny transistor that I'm having here. And let me present it to you. Let me show it. And it's already jumping to 2.3, but actually it's 2.4. It's 2.3 now, but it got to 2.4, probably because it's very cold right now. But as you can see, and it will increase a little bit more and more. You see, it's already increasing right now. But it will get to 2.4 or 2.44 actually it got. And I'm getting, with this setup, what you are seeing here, I'm getting 12 watts dissipated over that tiny transistor. So with this circuit that you are seeing here, you can test a transistor and its heatsink that it must have on it. So this is a very good transistor tester, power transistor tester, and the heatsink that it must have over the transistor, how bigger heatsink it should have. But you can see this pointed or dotted line that I'm having here, and this pointed line is actually is the fact that I actually link it to the power supply, to this 5 volts here, to test this transistor. But you can use this input here another way. You can test another circuit board or another component, like my voltage regulator, that all this circuit was originally intended for that, to test it at different amperage values and different power values, or increasing power over that voltage regulator. So this is the role of this circuit, is a variable current and power load, pretty much what I'm having here. It's a very good circuit. I really like it. It's very user friendly, like the guys in the AAC forum. So as you can see, it increased already a little bit. It's 2.38 now, and it will gradually increase as well. So this is a bit too hot here. It reached probably this 70 degrees already. Yeah, you can hold your finger, but not too much. And here, this is warm-ish, but not. It's slightly warm right now. It's slightly warm. It's not hot, but it will become hot after a couple of minutes. So as you can see, nothing blew up. You can see the reading there, clear as day. You see 2.39 and 2.4. Come on, 2.4. Probably it's this resistor that is losing a little bit of power over. That's why it's increasing. That thing is increasing. You see 2.4. Come on. It was for a little second. There, 2.4. And it actually, in my 10 minutes test, it did increase to 2.44. And but very slowly. This time it increased a little bit fast right now, but after a while it will increase very slowly after the 10 minutes. Okay, thank you very much for watching. I hope you like it. I hope you learned what it takes to actually drive a transistor at more wattage, at more power and more current than when it is naked, like this. When usually a transistor is made, especially this medium power transistor, this is not a good naming for them. It's not a power transistor, it's actually a medium power transistor, because there are higher power transistor than this. So bigger, much bigger power, and bigger sizes than this one as well. As my friend, its original circuit that it had, and I will show a picture of it, it had that bigger transistor as well on it. And so this is what it takes. This is how much cooling it takes, and even more cooling than this, if you want bigger wattage and bigger current to pass through this tiny little thing here, from here to here in the middle. Make an abstraction of that hole for the screw. All what is happening is here, from here to here, from that point. So yeah, a very important lesson if you want to drive more current and more power through this, or medium power transistors, like in my case that I'm having this BD681. I hope you like my video, and leave a like, and see you later with another cool movie. But this one was a very cool experiment that I did, and I'm very happy with the results. Okay, see you later, and bye-bye from your favorite artist electronics, Mr. Q12. Bye-bye.